In the realm of science and colossal privileged insights, the subject of what existed before the Big Bang has sparked conversations and intrigued thinkers for quite some time. This profound question not only challenges our understanding of the universe but also pushes the limits of human knowledge. Imagine standing at the edge of existence, gazing into the vast unknown, and contemplating what lay there before our universe was conceived. The event of the Big Bang marked the beginning of time, space, and everything we know. But was there a moment before this? Could there have been a state of nothingness, a calm before the grand cosmic expansion began? And if so, what was it? Or perhaps, something even more astonishing existed before time itself. As we delve deeper into this mystery, science takes us on a journey beyond the universe's origin, into ideas that challenge our very understanding. Physicist Brian Cox, known for his research into the wonders of the cosmos, suggests that something unexpected may have existed before the Big Bang. He urges us to rethink our concept of reality and existence. In this exploration, we will break down the science, the theories, and the astonishing mysteries that might explain what came before everything. We will examine ideas such as cosmic inflation, quantum fluctuations, dark energy, and even multiverses. The answers we uncover might surprise you, but they could also offer new insights into our place in the universe. Get ready to dive deep into a world beyond imagination and science, where the unknown still lingers in the shadows, leaving researchers both amazed and, at times, unsettled. Let us explore what existed before the Big Bang and why these theories challenge everything we thought we knew. To understand what may have existed before the Big Bang, we must first carefully examine what the Big Bang truly was. Scientists define the Big Bang as the moment when the universe became phenomenally hot and dense, expanding rapidly to create all matter, energy, and fundamental forces. When we look at the night sky, we see evidence of this explosive beginning, with galaxies spreading outward from an initial singularity. But why did this happen? And was there a time before this dense, hot state? According to the theory of cosmic inflation, there was indeed a before, and it was far from empty or peaceful. Cosmic inflation suggests that before the Big Bang, the universe existed in a state that was cold, empty, and relaxed, similar to an enormous vacuum. However, this vacuum was not truly empty. It contained a vast amount of energy that fueled the rapid expansion of space itself. This expansion, known as inflation, happened so quickly that it essentially laid the groundwork for everything that followed. In a fraction of a second, space stretched at incredible speeds until the expansion slowed, and the energy transformed into matter, particles, and the forces we recognize as the Big Bang. But what was the nature of this energy? Why did it suddenly cause the universe to expand? And why did it stop? Scientists believe that cosmic inflation created multiple regions of the universe, each experiencing its own Big Bang. Imagine an endless fabric stretching, with tiny bubbles forming throughout, each bubble representing a universe, including our own. This concept, called the inflationary multiverse, suggests that there could be an infinite number of Big Bangs and countless universes. Our own universe might be just one of many. This vast, mind-bending reality challenges our understanding of the universe itself and raises the question, what else is out there? The idea of nothingness before the Big Bang is more theoretical than factual, at least according to our current understanding. Even if we were to remove all energy, particles, and radiation from the universe, it would still not be truly empty. Our universe is filled with dark matter, dark energy, quantum fields, and fundamental forces, forming an intricate tapestry of something even in its most vacant form. Even if we imagine stripping away these forces, leaving behind a dead void, the universe would still generate new types of energy. This alone baffles scientists, as it suggests that true nothingness may be impossible within our cosmic framework. As we probe deeper, we discover that space itself has properties, rules, and constants that prevent it from being entirely empty. Imagine creating a region with absolutely nothing in it, no particles, no radiation, and no energy, except for quantum fields and fundamental constants. These would still exist, implying that even nothingness has properties. For example, there's a phenomenon called zero-point energy, which represents the lowest possible energy state of quantum fields. In this state, particles can still momentarily appear and disappear, creating a ghostly echo of activity even in what should be empty space. This challenges our very concept of a true vacuum and suggests that, even before the Big Bang, something existed, something that scientists are only beginning to understand. One of the most astonishing theories in modern cosmology is the possibility of eternal inflation. If inflation could give rise to our universe, it's possible that it could continue indefinitely. Brian Cox describes a vast, ever-expanding multiverse where new universes are constantly being born. Imagine each Big Bang as a spark igniting another universe, while inflation continues in other regions, creating countless new universes. This process could, in theory, go on forever. The idea of infinite universes gives rise to a fascinating concept, a fractal universe, where each new universe could potentially create its own Big Bang. Each universe exists as an independent domain, unaffected by the others due to the rapid expansion of space. For scientists, this theory is both exhilarating and unsettling, as it suggests an endless multiverse with no definitive beginning or end. What if our universe is just a small fragment of a vast, ever-growing cosmic structure? What if the unsettling truth is that there is no before or after, but rather an eternal cycle of universes forming and dissolving? Our understanding of nothingness shifts when we consider quantum field theory. According to this theory, the universe is not just a collection of matter floating in space, it is a complex network of energy fields that fill the cosmos, interacting to create everything we observe. These fields are like invisible oceans, with particles behaving as waves or disturbances. Even when these fields are at their lowest energy level, known as the vacuum state, they remain active. Particles can momentarily appear and disappear, borrowing energy before vanishing again. This phenomenon results in virtual particles, entities that briefly exist and then disappear, leaving behind only a faint memory of their presence. The existence of virtual particles challenges the idea of a true void. Imagine a universe where all matter, radiation, and energy were removed. Would it be truly empty? You have complete nothingness, as per the quantum field hypothesis. You wouldn't, indeed, even in a vacuum, as fields would remain dynamic some of the time, creating transient particles. This consistent development in what ought to not be anything proposes that the universe doesn't perceive our idea of void. The fields and powers continue filling the universe with a secret energy that forestalls outright nothingness. Pluto is a far-off and subtle, more straightforward planet that was once a piece of our close-by planetary framework. Anyway, progressing, upsetting declarations by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight. They recommended that this cold world is on a potential crash course with Neptune. Yet how is it that this could truly work? Furthermore, what may be the aftereffects of such a huge event? Are we seeing a dumbfounding, tremendous inconsistency, or is there another thing to this approaching, ceaseless misfortune? Go along with us as we look at the expected consequences of a Pluto-Neptune influence. Pluto, a previous planet that was renamed as a dwarf planet, remains a subject of interest and study in the tremendous universe, as shown by ongoing suppositions from leading experts. Pluto's circle is unsafely near Neptune's, and astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising the alert about a possible dangerous mishap between these two planets, which could address a monstrous gamble to Earth. Yet how is such an event even conceivable? Pluto's journey around the Sun is not normal for that of any other planet in our nearby planetary system. It requires a stunning 248 years to complete a solitary circle, and since its discovery in 1930, it hasn't even completed one full revolution. Anyway, the interest doesn't stop there. Pluto's circle is set apart by its especially circular shape, meandering broadly from the practically roundabout circles of the major planets. What makes Pluto's circle a lot more astounding is its tendency, which is 17 degrees to the ecliptic plane. The way Pluto follows its path is essentially more unpredictable compared to other planets. This propensity and eccentricism add layers of intricacy to its orbital course of action. Possibly, quite possibly, one of the most charming pieces of Pluto's circle is its convergence with Neptune's. For around 20 years in each circle, Pluto actually moves nearer to the Sun than Neptune, opposing what we could anticipate from their positions in the planetary framework. This prompts the typical inquiry: why hasn't Pluto slammed into Neptune? The response lies in the gravitational impacts of different planets. The assessment of Pluto's circle began not long after its discovery. Initially, stargazers endeavored to sort out its unique way. Dissimilar to other planets, whose circles lie genuinely near the ecliptic plane, Pluto's circle stands out with its profound tendency and flighty shape. The secret developed with the acknowledgement that Pluto's circle does indeed cross Neptune's. The strength of Pluto's circle, notwithstanding these multifaceted design issues, is proof of the intricacies of divine mechanics. The three-body issue in space involves deciding how three objects in space, like Pluto, Neptune, and the Sun, move and impact each other with their gravity. It's like attempting to foresee where they will go in light of where they started and how they pull on each other. For Pluto's situation, this issue shows how its circle, Neptune's circle, and the Sun's gravity all work together in a complicated manner. The terms non-simultaneous libration, orbital precession, and VZK wobbling are vital to this riddle, as made sense of by astrophysicists. What keeps all planets in their circles is non-simultaneous libration. As to Pluto and Neptune, this term basically implies that when Pluto crosses Neptune's circle, it is situated something like 90 degrees away from Neptune. This spatial division is critical in keeping their circles from meeting. Orbital precession, on the other hand, alludes to the upward development of a body in its circle. For Pluto, this implies that when it comes nearest to Neptune or some other giant planet, it is situated far above their orbital plane, adding an additional layer of security from possible impacts. One more key factor in this is the VZK wobbling, named after three analysts, Zell, Kai, and Kaku, who examined how objects move in space. It involves how three space objects, like Pluto, Neptune, and the Sun, pull on one another with their gravity. This pulling impacts how they move. For Pluto's situation, the VZK wobbling assists us with grasping the reason why its circle near the Sun is so surprising. Regardless of Pluto's circle seeming tumultuous, this wobbling helps keep it moving easily over stretched periods. The VZK wobbling shows that, in spite of the fact that things in space appear to be wild and capricious, patterns and rules keep up with some control. These forces help keep Pluto's circle stable, ensuring that it doesn't impact with Neptune or float off kilter. This three-body issue is critical in understanding how these circles change because of the manner in which space objects pull on each other. Concentrating on this assists us with learning more about Pluto, our planetary system, and indeed, even far-off worlds and their stars. Mathematical recreations in the last part of the 1980s uncovered that, in spite of the settling properties, Pluto's circle is as a matter of fact flighty, with minor deviations in starting conditions leading to enormous contrasts over hundreds of years. Anyway, these eccentricities of Pluto's circle have been found to maintain stability over incredibly significant time frame scales. Checking the interruption from later programmed assessments has assisted us with understanding how the giant planets, like Neptune, Jupiter, and Saturn, influence Pluto's circle around the Sun. Neptune has a unique relationship with Pluto, where for each 2 circles Pluto finishes around the Sun, Neptune finishes 3. This relationship helps keep Pluto's circle stable. Anyway, Neptune isn't the only one at work. Jupiter's gravity likewise plays a gigantic role in balancing out Pluto. Pluto's circle, Saturn, also contributes. These investigations show that Jupiter's huge gravity is sufficient to guarantee Pluto stays on a consistent path for quite a while, possibly even for a long period of time. So perhaps Neptune, Jupiter, and Saturn are collaborating to make Pluto continue to move securely through space without running into trouble. These characteristics are vital to keeping everything set up in space. Without these instruments, the solar system, as far as we might be concerned, would be a much more violent spot. Bodies like Pluto could slam into others or be launched out from their steady circles, setting off a chain reaction with other divine bodies. For Pluto, particularly with conversations about it possibly crashing into Neptune later on, understanding its circle is significant. This gives a more clear image of the dynamic nature of the close-by planetary framework. The instance of Pluto shows how even the most apparently unsteady circles can reach a condition of equilibrium through the complex connection of gravitational forces and orbital mechanics. It also highlights the significance of consistent perception and investigation of these peculiarities to better comprehend our position in the universe. Investigating the profundities of space frequently drives us to defy the bizarre nature of heavenly bodies, and Pluto's circle is an optimal illustration of this anomaly. The concept of orbital confusion, which alludes to the delicate reliance of a heavenly body's circle on its underlying circumstances, is plainly shown. For Pluto's situation, this implies that even slight changes in the diminutive planet's situation or speed can decisively change its drawn-out circle. Utilizing computerized recreations has been immensely helpful for researchers in sorting out how Pluto moves in space. These reenactments utilize complex arithmetic to display how Pluto and other space objects, like Neptune, pull on each other. By tweaking little subtleties in the reenactments, space scientists can see how even minute changes can make a huge difference in where Pluto winds up.